I can have no.
Good evening, everyone. Welcome to the makeup class once again. My name is Prince Wilson, and I'll be taking you through today's session. Please let me know if you can hear me or not. Okay. So then, since from the reactions, I assume that you can't hear me, so we may start the session in the name of God the Father, the Son, and the Holy Spirit. Amen. So let's do a quick recap of what we studied yesterday. Since we were following through to the end, then it just needs some speed reviewing, and then we continue from where we left off. So yesterday we looked at um, okay, let's proceed. So yesterday we looked at random experiments. We looked at what probability was, how it was defined, and the agents of probabilities, and then the properties of probabilities as well. So we talked about experimentation, and we said the process of observation is what we call an experiment. We talked that the number of times you repeat an experiment is called a trial, and then a random experiment is one whose outcome is not known with certainty or cannot be predicted with certainty, like when you toss a die or when you toss a coin or when you're picking a random ball from a bag or when you're picking a card from a deck. You cannot tell with certainty what exactly is coming, provided all instances are fair, then you cannot tell. So we call this one random experiments. the outcomes, or what are the possible results of a random experiment. For example, if I toss a coin, the head I get or the tail I get is what we call an outcome. So then what comes out of an experiment is the outcome. And then we have other terms like events or the sample space. The sample space is a set that contains every possible outcome in an experiment. We mentioned that, for example, if I'm tossing a coin, I may get a head and a tail, or a head, a tail, right? These values are what make up the sample space when they are put in a single set. Now, combining one or more outcomes is what gives you what we call an event. So, for example, if I take a sample space of tossing a die, the probability of me obtaining an even number is an event, or obtaining an odd number is an event, because that will be a collection of different individual, what do we call it, events, right? Now, sometimes the events may contain just a single outcome, and then we call this one an elementary event, or sometimes it can contain multiple outcomes as well. We also mentioned that inside a given sample space, there may be what we call sample points. A sample point describes a particular value inside the sample space. Sample point. So here's an example. So if I have a Ludo die, I toss the faces as 1, 2, 6, and then one of the sample points in there can be what we call it 4. Probability of obtaining a 4 can be a sample point, etc., etc. So a set A is called a subset of B, and then is denoted by A is a subset of B if every element of A is also an element of B. We mentioned that yesterday. So when we say one set is a subset of another, then it means all the elements present in that set are also present in the other set. And these are some examples. We talked about the probability, what are the possible outcomes when you start tossing a coin and you count how many times you have to toss to get ahead. And we said you may toss once before you get ahead, or you may toss 2 times and you'll get ahead later, or you may toss 3 times before you get ahead, etc., etc. We also mentioned that some other examples have to do with like when you are drawing cards from a bag. We mentioned that, for example, if you're drawing a card without replacements, and then we have to find the sample space. In other words, what are the possible outcomes you can get? Since you're not replacing a card, you may get 1 on the first draw, and the second draw might be a 2. You may also pick 2 on the first draw, and the second draw might be a 1. You may also pick 2 on the first draw, and the second draw might be a 3, etc., etc. That gives us 12 possible outcomes. And we also know that when we draw a card and we replace it this time, the possible outcomes will now change because we can pick one card twice. So we can have an outcome like 1, 1, 1, 2, 2, 2, etc., etc. Okay. So now that's what you can see here. Now, we also mentioned that if we take a lifetime of a transistor, for example, how long the transistor can function before getting damaged, since it's time we are measuring and we know time is continuous, this particular value can take on endless range of values from 0 to positive infinity, and then it's practically endless. And even if we assign it within a particular range, so for example, if I told you that the transistor can survive for between 1 and 2 minutes, you cannot tell what exactly how much time it will take. You don't know whether it's 1.1 minutes, 1.05 minutes, or how much time it takes. So we say it's continuous. Discrete sample space only take on finite countable, what do we call it, sets of values, or even infinite countable sets of values. So for example, I'm trying to count how many people attended the program. This is what we call a discrete value because I am counting. So whether the counting is endless or the counting has a particular end, as far as the values can be counted, then we say it's discrete. Wherever continuous is mostly assigned within an interval and then it's mostly measured, and it's also mostly real numbers, not always, but mostly real numbers. That's your decimal numbers and whatnot. Random variable is a variable whose values are numerical outcomes of a random phenomenon. So we just explained that. We may assign random variables as x, a y, or a z. So for example, if I toss a coin, right, and I say the probability of obtaining a head is a random variable x, what this means is that the probability of obtaining a head, which has been defined as x, is going to be how many chances I can get my head. That's going to be 1 out of 2, right? So random variables are assigned to random, what do we call it? Random outcomes inside a random phenomenon or a random sample space. Typical example of a random variable is the outcome of a coin toss. So if the random variable y is the number of heads we obtain from tossing 2 coins, y could be a 0, a 1, or a 2. So then maybe let's say this is y1. Probability of y1 is going to be how many zeros you see here over, how many possible outcomes there are all the way to this, blah, blah, blah. So we talked about this yesterday. Discrete random variables examples include the Friday night attendance at the cinema, number of patients in the doctor's surgery, the number of defective light bulbs are in a box out of 10. So things you can easily count. Whereas continuous talk about things you can measure like your height, your weight, amount of sugar in an orange, or the time required to run a mile. Chance and assessment of risk. Okay, we talked about applications of probability in real life. We talked about how you can apply it as a loan officer in investments, calculating profits and comparing that to losses, etc., etc. Probability is the measure of likelihood of occurrence. So how likely an event is to occur is probability. We thought that probability are always numbers from 0 to 1. If any number is less than 0, it can be a probability. If it's greater than 1, it can be a probability. So if a probability is impossible, we say it has 0 chance of occurring. And if a probability is 1, we say it is definitely going to occur. Probability of an outcome is interpreted as the limiting value of the proportion of times the outcome occurs, blah, blah, blah. This is the relative frequency definition, which states that for any given value, its probability is just the value over the total number of possible outcomes. So for example, if we assign a probability of 0.4 to the outcome that there is a defective item in a production batch, then we interpret this as approximately 40% of production value or products from this production batch, 40% of them are defective or are not in good shape. All right. This is the formula that defines the relative frequency of probability. So then this one, it gives it, you may be asked a question that which of these defines the relative frequency of probability. So look at it carefully. The limiting value of n approaching possible positive infinity, the numerator is the number of ways the value can occur over the sample space. This is the same as what we know concerning other probabilities. It may also be written as number of favorable outcomes of A over total number of outcomes, still relative frequency. And then going further, we have shown some examples. So like, for example, probability of obtaining a 60. When we know that one person got 60, is going to be 1 out of the total number of people who took the test. That's going to be 1 out of 63. Probability of obtaining a, also, let's say, probability of obtaining a 90 is going to be 5 out of 63, as you see here. Probability of obtaining a mark less or equal to 83 means probability of getting a 60 or 75 or 78 or 80 or 83. What this means is since we are doing probability or, you can just go ahead and add the individual probability. So that's going to be 1 over 63 plus 3 over 63 plus 4 over 63 plus 5 over 63 plus 7 over 63. And that's what you see down here. That gives you 0.31. We also mentioned that the probability of any given event, when you want to define as a classical definition, the probability of any given event is the number of the events inside the sample space over the total number of events in the sample space. So for example, probability of A is number of A over the total sample space. So I go into a class, what's the probability of picking a student that is where it's a boy? I just take the number of boys over the total number of students in the class, and that's what you see, a number of ways that A can occur over the number of ways that the sample space can occur. Right, so now there are 5 balls in a box. 3 are red, 2 are black. The box is shaking. A ball is selected without looking. What's the probability that it's red? That's going to be the number of red balls. That's 3 over the number of balls in the bag. That's 5. If you ask for black, it's going to be 2 over the number of balls in the bag. That's 5. You can write that as a fraction or a decimal or whatever. Now, another example says in a group of 400 college students, there are 170 science majors and 230 non-science majors, blah, blah, blah. What's the probability of finding a science major? That's just going to be the total number of science majors over the total number of students, 170 over 400. Or the probability of selecting a woman is just going to be the total number of women, which is 175, over the total number of people in the class, which is 400. The probability of selecting someone who is neither a woman nor a science major, so those who are not women are definitely men, and the men that are not science majors are in the category of non-science majors. And the number is exactly 110, as you can see here. So the probability of selecting a person who is not a man and a non-science major as well is 110 over the total. That's 400, and that's what you can see right here, like this. Okay. You look at the axioms of probability. The first one says that every probability is from 0 to 1. It cannot be greater than 1 or less than 0. It must be from 0 or in between 2 values. We also mentioned that the probability of any event in the sample space occurring, or the probability of the sample space occurring, in other words, the probability of having an outcome in an experiment is a certainty. So there's no way you do what do we call it, an experiment without getting an outcome. So that is saying that the probability of the sample space S occurring is equal to 1, whereas the probability of an event happening outside the sample space is always a 0. So you cannot have 7 when you toss a fair die on a fair die. In performing an experiment, we assume that the results will be one of the simple outcomes. In other words, we assume that the event S will always occur. Now, equation 3 says that when you're combining two probabilities and then they are mutually exclusive, it means they have no intersection. All you need to do is just add A and B together. So you just add both probabilities and you're done. So always check if the two events are without intersection. If the sample space S is not finite, then A must be modified as follows. So for example, if I want to combine a lot of events that are what we call it a lot of events that are mutually exclusive, all I need to do is add their probabilities together without subtracting any intersection, since we said they're mutually exclusive. So let's say you have 1, 2, 3, 4, 5, 6, 7, about 1,000,000 events. You just add the probability of A plus that of B plus that of C. So then as you can see here, it says summing all the probabilities of A, starting from the first value, 1, all the way to positive infinity, as you can see here, top here, like this, all right. Let's move here. So this means that, for instance, if A1, A2, A3 are events that cannot occur at the same time, this means they're mutually exclusive, or they cannot occur simultaneously, then the probability that one among them will occur is the sum of their probabilities. So for example, if the probability of either a coin and either a 2 or a 6 in a row of a die is 1 over 6 plus 1 over 2. You see the keyword here, or. So it's just the probability of rolling a 2 plus that of rolling a 6. Now, I want you to take note of the fact that the probability of rolling a 2 and a 6 are independent of each other. Like there is no common ground between them. However, for other events, right, you can actually have common ground between them. And then for such event, that's when you have to subtract the, what do we call it, intersection. All right. So for example, let's say a question asks us to do this. So let's say we have a question that tells us that we have to calculate the probability of rolling perhaps a 1. Okay, probability of rolling an even number. Let's write probability of rolling an even number here as probability of E, okay? And then probability of rolling, what do we call it? Perhaps an odd number. So let's use an O for that. On the face of a die. Remember that the values on the face of a die include this. What is 1? There is 2. There is 3. There is 4. There is 5. And also there is 6, like this. So all these are the events that you can get when you roll a standard die. The probability of obtaining an even number is just how many even numbers you see here. And I believe we know that already. 2, 4, 6. Over the total number of possible outcomes or the sample space. So that's going to be the probability of an even number, P of E, is how many even numbers are there, which is 3 out of how many numbers are inside the sample space, which is 6. Simplify this and then you have the value 1 over 2 or 0.5. So 1 over 2, like this. Now the probability of you obtaining an odd number. So now let's see what values are the odd numbers. The odd numbers include every number that cannot be divided by 2, remember, like 1, like 3, and also 5 here. These are the odd numbers, right? The probability of obtaining an odd number is going to be how many odd numbers are here. That's exactly 3 over how many values are inside the sample space. That's 6. And that also brings us to 1 over 2. Now, I want you to take note of the fact that when we took the set for even numbers, you see that the set for even numbers has these values: 2, 4, and also 6. Like this. And then the set for odd numbers, that also has these values right here. Let's see what we have. 1, 3, 5. Now you realize the way these two sets share no similarity. Like the values in here are independent of the ones in here. We call these two sets mutually exclusive. It means they share no common ground. Therefore, if I want to find the probability of getting an even number or an odd number, it means the probability of one of them happening. So, or remember that union, probability of getting an even number like this, or union like this, an odd number like this. So the probability of getting an even number or an odd number, since they are mutually exclusive events, is just going to be what I get when I add these two sets together. right? So that's just going to be probability of even number 1 over 2 plus probability of odd number also 1 over 2. And that gives me exactly the number 1 if I add right. So it becomes 2 over 2, which is the same as 1 like this. What this means is that you see on the face of the die, there is actually 6 outcomes. And also those 6 outcomes, 3 are even numbers, 3 are odd numbers. So the probability of you getting an outcome that is one of these guys is literally possible, like it's 100% possible. If I go to the bag, I either pick an odd number or an even number. So there is a 100% certainty. And that's why we are getting 1 in this case, and that's what it means. Now, let me change the question a little. And this time, instead of dealing with even and odd numbers, let's deal with something like even numbers and prime numbers. Did I just wipe out my sample space? Okay. Okay. So now with this, we can now work some examples, but then this time, let's see an example that says we have to find probability of even number and also probability of maybe a prime number. So let me use P of P. Okay. So now we know that prime numbers are numbers that cannot be sorry, that have exactly 2 factors, that's 1 in themselves, right? So now all the prime numbers here, the prime numbers inside this set include every number that has only 2 factors. So we start with the first one, that's 2, followed by 3, followed by 5. These guys are the prime numbers inside the sample space. Probability of getting a prime number is going to be how many prime numbers are here, and that's exactly what 3 out of 6 outcomes, and that gives us 1 over 2. However, if I want to find the probability of E and or probability of P, so probability of getting an even number or a prime number, like so, probability of getting an even number or a prime number. If I want to find the probability of getting these two, then I'm going to have to combine these two probabilities here. That's probability for getting a prime number, and that's for getting an even number. But you see, there is a catch. Currently, how many even numbers do you see here? 3, and then there are 3 odd numbers, prime numbers too. But then there is one number that repeats at both places, 2 and 2 here. So yesterday we mentioned that if the two events have an intersection, you have to subtract the number of times the intersection happens. Over here, you realize the intersection is just one value, right? And then since it's just a single value, it means the intersection is 1 out of the 6 values that are present on the board. Therefore, the probability of A union E is going to be probability of A, and probability of E, which is what? 1 over 2, plus probability of the next one, which is this guy, which is also 1 over 2. But since there is an intersection and then it means the events are not exclusive mutually, we have to subtract the intersection from it. Remember, the intersection is 2, and 2 is 1 out of 6 faces of the die. Remember that this is 3 out of 6, this is also 3 out of 6, and this 1 out of 6. So when I combine 1 over 2, 1 over 2, I get exactly 1, right? And I do 1 minus 1 over 6, and let's see what that gives me. That gives me 5 out of 6. So now you see there's a difference between the working we've done here and what we did earlier. The first one said, since they were mutually exclusive, according to equation 3, if they are mutually exclusive, all you need to do is combine them to find their joint probability. However, if they share an intersection, after combining them, subtract the intersection. That is all the third property means. Okay, let's proceed. Do we have any questions so far? So I'm taking too much time on the recap, and then I don't want that. So we can go the properties of probability said if an event is probability A, then the possibility of it not happening is 1 minus that, since 1 describes total probability. And we said that the second probability says that for events that are not present in the sample space, they are impossible to happen, so the probability is always 0. We also mentioned what I just described, that the union or addition rule says that if there is an intersection, after combining two elements, you have to subtract the intersection, the number of times the intersection happens. So if there are 4 intersections, subtract the probability of the intersection happening 4 from the, what do we call it, sample space. All right. Finally, the theorem, finally, this one says if we have 3 separate, so this is the first theorem of probability. By the way, we've done 3 properties. We have done 3 axioms, and then let's look at theorem 1 of probability. There are other ones too, Morgan's, and then etc. De Morgan's theorem. They also help in working it. We'll look at De Morgan's one soon. Now it says that if A, B, and C are 3 events, then the probability of A and B and C, or A plus B plus C happening, since they mentioned here, it should be probability of A plus B plus C. And after doing that, we subtract the intersection of A and B, also subtract the intersection of A and C if there is some, and also subtract the intersection of B and C if there is some. But finally, we have to add the probability of all 3 events happening as an intersection. That's the one here. So you subtract the individual intersections and you add the joint intersection. That's if there are more than 2 events. So if there are 3 events, you do it like so. Okay, if there are 4 events, you modify it accordingly. Okay, we worked these examples yesterday. Now let's look at what De Morgan's law is about. So let's try to use De Morgan's law to see how this particular working can be done. Now De Morgan's law is a function that distributes, what do we call it? It distributes multiplications over additions and additions over multiplications. So for example, what you can see here currently, the intersection here in probability represents a multiplication, basically just like Boolean logic. So then if we have probability of A intersection B, De Morgan's law says we can rewrite it as A union B, all complements. So we are taking into consideration the complements, mind you. So according to De Morgan's law, if we solve this, the answer we are going to get is going to be the same as what we get when we solve this. So it distributes intersections, it distributes, what do we call it? Multiplications over addition and additions over multiplications. And then it works with their complements like so. So then yesterday, what we were solving, this is another alternative way we can solve this particular question. So we can just take probability of A, add that to probability of B, and finally subtract probability them from 1 to get their complements. Okay. So in other words, it is the same as what we should get over here in this working, like so. All right. Then you can see clearly that the 2 workings even actually give the same answer. This one gives you what, 1 over 3. This one also gives you 1 over 3. You see, they already are saying that if we distribute this intersection, we can distribute it over a union. In other words, we can distribute the multiplication over an addition, and then these two become the same statement. Therefore, if this one results in 1 over 3, this also results in 1 over 3. Alternatively, you can state that we can also spread values like this, which are rather what we call it unions over intersections. And when we do that, we spread the complements among them. So this is De Morgan's law, basically. So I think that's 2 theorems, right? All right, we continue. So, okay, yeah, that's that. So now in the toss of a fair die, find the probability that the result is even or divisible by 3. So you see it says even or divisible by 3. Let's consider what the sample space is. Now see what the values they have given us so far are. They are telling us that for A, since let A be the event that the result is even numbers include 2, 4, and 6, whereas the multiples of 3 include also 3 and 6. Then the probability of A union B will have an intersection. You see that intersection is 6. That occurs in both sets here and here. So if we want to find the union, we combine A and B, and when we are done, we subtract the intersection, which is 6. And 6 has a single chance out happening out of the whole 6. And that's what you can see happening over here. And that gives us the end value of 2 out of 3. Let's move faster. So the rest of it, we studied all this yesterday. So I'm jumping right through, and expectation. So this is where we got to yesterday. So now let's see what expectations are. Expectation is if x is a random variable distributed as p of xi or f of x, then the expected value of x, which will be denoted as e of x, is defined as, so for discrete random variable, the expected value of x is given as the value itself times its probability. So you see it says xi times probability of x. So for discrete random variables, and that's what we'll be tackling today, is going to be x times the probability of x. Whereas for continuous, it has more to do with what we call it differentiation a little. And as you can see here, for when we get there, we will look at it. But then it will be treated more in lesson 3B. But for now, we cover the basics of it. That is in discrete probabilities or discrete variables. Okay, let's continue. Now it says, consider a class of 24 students, and let's suppose that 5 of them are 19 years old, 7 are 20, 10 are 23, and 2 are 17. Let us denote by U the mean age of the class. So you see the mean age is going to be sigma fx over sigma f, right? I hope you remember these things. So if you are taking for a value like this, the mean is the same as the average. However, for these ones, we are going to do sigma fx over sigma f, right? Remember what sigma fx is? It's what you get when you multiply the class or the score by the frequency. So now we are talking about the ages of people. We said 5 of them are 19 years old, right? So then the mark is 19, and the number of people who are 19 is 5. So as sigma fx, that's summation of all the f values times the x values. So max times frequency. 19 times 5 for days, blah, 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 all the way to the end. This gives us a combined value of 20.79. And this is what we call the mean. So you can be asked to set for the mean actually in your workings. Now, it says let x be the random variable taking the distinct ages as value. So now let's say x, as we mentioned earlier, random variables, we can assign them to probabilities. So now let's say all the ages here are assigned to the value x. And we define x1 as the first age, 19, x2 as the second age, 20, x3 as the third age, 10, 23, x4 as the last age, 17. And then the probability law is giving us the probability of finding an event. If that event is going to be x1, then it's going to be a number of ways x1 can occur over the sample space. I believe we know that already, right? So how many ways can f1 occur? There are 5 people who are 19 years, therefore 5 out of 24, which is the total sample space. The probability of x2 occurring is going to be how many ways x2 can occur. Remember that x2 is the second age, and which has been given to be what? Let me see, 20, right? 7 people can be 20 years old, so that's going to be 7 over 24 all the way to the end. This one here, the table you are seeing down here, can be used to compute these values here, like so. Here. So x here. So it says we can summarize the probability law in the following table as the probability for any given value. If the value is x1, then it's going to be 5 out of 19, 5 over 24. That's probability of getting a 19. If the value is x2, then it's going to be 7 over 24. It's going to be x3. How many people are 23 over 24, etc., to the end? Right. Let's proceed. So this is what we call mathematical expectations. Okay, we will look at other examples too. We will actually work one on our own. I think I prepared some. If it's still available, I'll pull it out. If not, I'll just let ChatGPT generate a quick question so that you tackle your answer on it and then we work it together. All right. So this one says that we set a sample space as the class of these students, and then the following graph x is given as this one is going to be a distribution over a graph, by the way. But then pay no mind to this. This will be covered in detail in lesson 3B. Don't be confused by the symbols. They're just assigning them to values. All right. Now let's this one define the age of a student here, this W symbol here. It defines a random variable. Now the probability that is used on this sign here, the sample space is the frequency of occurrence. Okay, so now for each event, we classify its all of them inside the elements are 1, 2, 3, and 4. The probability of X being any of them is the frequency of occurrences of the age in the class. What this is doing is explaining what you saw here earlier. So then the probability of we obtaining a 19 is the frequency of 19, which is literally 5 over the total number of people. So relative frequency 5 over 24, etc., etc., to the number of rand. Now it says, therefore, through these notations, we have the following expressions of the mean. So then we say that the mean here is there's the summation X times P. So probability times this. This actually is also the same as the expectations. Now we are going to do a question right now, and then you see what expectations are all about. Basically, they just tell you just how likely an event is to happen if we keep doing an experiment. Just how likely an event is to happen if we keep doing an experiment. All right. So now we're going to look at one example for expectations before we move on to the next lesson. So now let's say I'm tossing a Ludo die. I'm throwing a die or something else, throwing a die. And we know all the expected outcomes are 1, 2, 3, 4, 5, 6. Now, the expectation formula says that if you want to calculate the expectation of getting these outcomes on a Ludo die, all we have to do is take for every value here and multiply it by its probability and then sum them up. So it's the sum expectation is equal to the sum of every given value times its probability. Where the first value is I is assigned to the first value as 1. And then it goes on till the set ends. Okay, so in this case, we have 6 different values, right? So it starts from 1 and it goes to 6, like this. So then this is the expectations. Let's compute the expectation for a Ludo die in general. What are the expectation? What's the combined expectation of tossing a Ludo die? It might seem like a biased calculation, but it actually holds a lot of meaning. Okay, so now to find the expectation here, we just have to find the probabilities of all these individual events. So let's try that for these guys. So the probability of obtaining a 1 on the face of a die is 1 over 6. Probability for getting a 2 is 1 over 6 all the way to the end. What this means is that our expectation is going to be, for 1, we have 1 over 6 times the value itself times 1. And then we add that to, for 2, it's also going to be 1 over 6, but this time times 2. All the way to the end, right? This can be simply written as, since all the denominators are the same, 1 over 6 is going to give us 1 over 6, 2 over 6 is going to give us 2 over 6. 1 over 6 times 2 is going to give us 2 over 6, etc., etc. We are going to have it looking like 1 plus 2 plus 3 plus 4 plus 5 plus 6, all over the total sample space, which is 6. So what this means is that we've done 1 over 6 times 1 plus 1 over 6 times 2 plus 1 over 6 times 3 all the way to the end. Summing this up and dividing it by 6 gives us the expected value we are looking for. So let me see, if we do the calculation here, 6 plus 5 is 11, 11 plus 4 is 15, 15 plus 3 is 18, 18 plus 3 is 21. So this brings us to 21 over 6. And this is roughly equal to, I think, let me see, 16, 18, that's 3.5. So what this means is that the expected value at the end of tossing the Ludo die, given all these outcomes, is going to be exactly 3.5. So then the likelihood of any of the outcomes occurring, and not a probability actually, not a probability, but then the expected value is 3.5. That's the whole idea. It becomes hard to explain what the expected value is and how it is different from the probability, but then they share a close relation. But for now, just know how it is worked on, and then when it is when we are doing expectations in detail, then perhaps it will be more clearer then. All right. So now we have come to the end of the first session. Are there any questions that you would like to ask before I move on to the next session?
Sir, please ask a question.
Yes, please ask.
The expectation, is it the same thing as the mean?
Now, for discrete variables, the expectation can be the same as the mean, as we demonstrated earlier. So you're not wrong to say the expectation is a mean in a discrete distribution. Mostly too, it applies to distributions that have equally likely outcomes and uniform distributions. For that one, it's clear that it is the mean. Yes.
Okay, thank you.
Yes, please. All right. Okay, so aside that, is there any more? I thought these slides were coming on. All right. So since there are no more questions, then I assume I can proceed, right?
Yes, yes.
Okay, but let's proceed. So in this session, we are going to focus on discussing conditional probability and also Bayes rule or Bayes theorem, right? Conditional probability, independent event, total probability rule, Bayes theorem, application of Bayes theorem. So far, all the lessons we've been looking at have discussed basic probabilities. Basic probabilities just express one event happening in a given probability. However, where we are moving on now is going to express one particular probability in terms of another. In other words, one probability is going to be the sample space. So as first we looked at finding a sample space of real values and then finding the probability of one of them happening. But this time we are going to have to use a given probability as the sample space, and this is what conditional probabilities are all about. Let's do a little reading and then we do some working. Probability plays a major role in everyday life and decision making, and it depends on one or more events of uncertainty. In this session, students will be introduced to conditional events and probabilities, independent events and probability, total probability rule, and Bayes theorem. At the end of the session, the students will understand dependent and independent events, calculate conditional probabilities of random events, and apply total probability rule and Bayes theorem for solving real-life problems. Okay. Now, suppose S is the sample space for an experiment with events A and B. Then, for experiments with equally likely outcomes, the conditional probability of A given B is the fraction of outcomes of B that are also in A. Let me take that again. For experiments, suppose that the sample space of an event is S with events A and B. Then for experiments with equally likely outcomes, then the conditional probability of A given B is the fraction of outcomes in B that are also in A. What does this mean? We are trying to say that, for example, you walk into a class, right? And then there are separate groups of people in the class. We have a group of people who are single, a group of people who are what we call as couples, and then a group of people who are also, let's say, boys, and a group of people who are girls. And then we ask you to not just find the probability of picking a boy, but picking a boy that is also a couple, like in a relationship, like the ideology. So then what's the probability of picking a boy, provided that that boy is in a relationship? This throws more light on what we see in probabilities. Normally, we are just looking at an individual and comparing them to the class. But this time, the individual group of boys, out of them, some of them are going to be single and others are going to be in couples. Like that, some of them are going to be in a relationship. What this means is that if we are to calculate this probability, you have to be able to isolate those who are single boys from those who are in a relationship. And that is going to be the probability you're focused on. In order to do that, you are going to have to express boys as part of those in a relationship. And that's literally what conditional probabilities is about. So then in a conditional probability, the total class or the sample space, right? The total class becomes one probability on its own. Let's just get into the calculation. Since only outcomes B is taken into consideration, in effect, B becomes the sample space. So then as we said, we are trying to find the probability of getting a boy who is in a relationship. This means the sample space is going to be the total number of people who are in relationships, right? Not the total number of people in a class, because you are just expressing the boy in terms of those who are in relationships. So the total sample space is going to be the probability of picking a boy inside the total number of people in a relationship. And that's why the sample space then becomes number of people here, or number of people who are in a relationship. So you can see it from the calculation. It states that you take the probability of picking someone who is a boy, A, also in a relationship, B, and you divide that by the sample space, which is the total number of people inside the relationship. So you can view it as this is your class. In your class, you have all these elements. A, you have B, you have C, you have D, you have E, you have F. And also, so let's say this is not your class, sorry. Let's say this is the people in a relationship R like this. And then let's say these are the boys in the class. Then the boys in the class, their names are boy A, boy B, and maybe boy E. And then we ask you, so we know that in the class there's a larger number of students there, but we are just considering picking a boy who happens to be in a relationship. Okay, so then the boys, so boy A, boy E, let's add more, boy K. So then let's say there is boy K, boy R, boy T over here like this. Now the probability of picking a boy that is also in a relationship, you see that there are several boys here, but then the only ones in a relationship are the boys A. As you can see, the set of people in a relationship is A, B, C, D, E, F. Boy B and boy E. Okay, rather boy C, right? So boy C is not given. Okay, boy E is also in a relationship here, so as you can see over here. The probability of picking a boy who is in a relationship will mean that I have to first pick a boy as well as the boy being inside the relationship. The English is not expressing it quite well, but the main part is say, sɛ mepɛ sɛ mefa bɛrima a ɔwɔ relationship mu a, anaasɛ mepɛ sɛ menya obi a ɔsan so wɔ relationship ne mu deɛ a, ɛnna ɛwɔ sɛ mehu obi a ne din wɔ ha a ne din san so wɔ list of couples ne mu. See, in order to calculate the probability of A giving B, in this case, probability of taking a boy given that he's in a relationship is going to be number of boys here who are also in a relationship. And that's what we call the intersection. So it means the person is a boy and he is in a relationship like this. So we are going to first have to know the intersection. And after getting that, we divide this by the total sample space. So the sample space is the total number of people in a relationship, and which in this case contains all these elements, 1, 2, 3, 4, 5, 6. Then the total sample space is all these elements here, and that is going to be number of people in a relationship. But the only people of concern to us are those who are boys in the relationship. So our probability is going to be number of favorable outcomes. That's the boys in a relationship over total number of people in a relationship. So you see, it's no different from the definition of probability we already know. Just at this time, the sample space and the individual events inside the calculation are all probabilities. I hope that is clear. So for this question, if we want to calculate probability of taking a boy, that is also in a relationship like this, then we are going to have to know number of boys in the relationship and divide it by number of people in the relationship, or probability of boys picking a boy in a relationship, good. Probability of picking a boy who is in a relationship over the number of people in a relationship. So now how many boys are in a relationship here? As you can see, it's exactly 3 out of 6 outcomes, right? So the probability of picking a boy who is also in a relationship is going to be, that's the B intersection R. So then there are 1, 2, 3 boys here. And then this is the intersection of them in a relationship here. That's ABE, sorry, C not included. And that's exactly 3 out of 6 outcomes. So that's going to be 3 over 6 for the intersection. And it says over R. In other words, divided by R. And R happens to be the sample space, which is the total number of people in a relationship. That's 6, right? So the probability of picking someone inside here, or the probability of picking anyone who is in a relationship, is going to be the sample space in this case. So for that one, we are going to have to know the total number of people in the class, right? But since I didn't include that, let's just assume there are 10 people in the class. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are going to have 6 out of the total number of people in the class, which is 10, like so. This is what the conditional probability is about. So it expresses one probability as a part of another. That is all. Any questions so far before we start solving the actual given examples in the slides? Please, if you have questions, ask them in the earlier stages so that they don't progress to when things start getting, things when you need the foundational knowledge and you're now like, hey, I do not understand this. That sets us back by a lot. So if you have questions, please ask now. Okay, forever hold your peace then. I guess we may kiss the bride. All right, so moving on. Similarly, we can define the probability of an event B given A as the probability of A intersection B all over the probability of A. So now take note of this. You see, the one that we are using as the predefined probability, in other words, the one that must happen before the other one does, is always considered a sample space. So if I am doing B given A, probability of A is the sample space. If I am doing A but giving B, then the sample space will rather be changed to probability of B, like so. The intersection doesn't matter how you write it. B intersection A is still A intersection B. So when you're doing B given A is the sample space. When you're doing A given B is the sample space. One thing you should do always is to simplify your explanation, just find your intersection separately, find the probability of A separately, and when you're done, divide them, and you're done. That's everything. Okay, so now it says that a very useful formula in computing joint probabilities. This one reverses the formula. So we are taking this and doing some change of subject. It says that in order to calculate the probability of A intersection B, you can manipulate this formula and then get probability of A given B times probability of B. How is that? According to change of subject, right? If you want to make probability of A intersection B the subject over here, we can just go ahead and then multiply this guy by this. So probability of A multiplied probability of B. And the only thing left standing on this side of the equal to sign is going to be probability of A intersection B. So the formula now becomes probability of A intersection B is equal to probability of A given B times probability of B, or probability of B given A times probability of A. Does this make sense? We are just doing change of subjects. Okay, so then if you are confused, this is basically what is happening. So we find an LCM. We are solving a linear equation. We find an LCM. So what's the LCM on all sides? Consider this as a fraction. It's also over 1. The LCM is P of A, right? So we are going to multiply through by P of A. So they are just telling you that if you manipulate the formula, you can leave this guy standing. So what we are trying to do here is eliminate P of A. So I'm going to first multiply through by P of A. So P of A times probability of B given A. Multiply this side too by probability of A, like so. And what happens is the probability of A here cancels the denominator over here. And that leaves us with probability of A intersection B standing alone. And our final answer is going to be probability of A times probability of B giving A. And that's what you are seeing here. This is what makes up the, what we call it, the joint probability of events formula, the intersection, sorry. So this is what gives us the intersection from the same conditional probability formula. All right, so now it says that for several events, if you want to find what we call it, the probability for several different events, then you're going to have to do what we just did countless times. So let's say for an event, and we are trying to find its probability of intersection or probability of the first one, probability of a second event, probability of the third event, probability of the fourth event, is just going to be, so A intersection A2 is going to be probability of A1 times probability of A2 given A1. A intersection A3, blah, 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 is going to be the same thing, and it keeps going endlessly to the end. But that's for when you have several events, and this is known as the multiplication rule. The multiplication rule. So when we come across an example that requires us to use it, then we do that. Let's proceed. We are making steady progress. Now, a survey about job attitudes. Okay, let me take this thing off my screen so I can see. Okay, a survey of attitudes about one's job yields the data in the following table. So then this is a table that describes the attitude of people towards their jobs. It says that their jobs are bus drivers, lawyers. Out of the bus drivers, 50 are happy, 75 are not happy. The total number of bus drivers is 125. The lawyers, we have 40 are happy, 35 are unhappy. And then the total number of lawyers is that, blah, 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 and all the way to the end. Now it says a person from this group is selected as random. Given that the selected person is a driver, find the probability that he is happy. Let's define these things, okay? So now it says that a person is selected as random, given that the person is a driver. So it means the given probability here is that the person is a driver. Let's say the driver is represented as D, okay? We are supposed to find the probability that he or she is happy. So then it means we are finding the probability of the person being happy coming from the driver's side. In other words, probability of finding a happy driver, something like this. Exactly. So probability of finding someone happy, given that the person is a driver. According to the formula, we know that it is supposed to be. Who can remind us of what the formula for this is, please? We looked at it on the earlier slide. Charlie, the formulas are simple ones. You have to memorize them, yeah?
Let me try.
Yes, please.
Okay, this one will be probability of H intersection D all over
Intersection D.
probability
Yes.
of D.
Oh, that's good. That's good. Wonderful. Was probability of D. Please, who is speaking?
This Kayun.
Oh, Kayun Bosu. I salute you. So then, as he has stated perfectly, since BD is what we are establishing as the given condition or the given probability, is going to be the denominator here. So all we need to do is know the parameters for probability of H and D. In other words, H intersection D and also the probability of D. So let's start by finding the probability of H intersection D. This means we need to find drivers, a person being a happy person, and also the person being a driver over here. And you see where those two things meet? This is it. This is the number of people who are happy and also bus drivers. So H intersection D is going to be, the probability of H intersection D is how many people who are happy bus drivers over how many people are also inside the sample space. Exactly. So the number of probability of finding a happy bus driver is going to be number of happy bus drivers. That's what do we call it? 50. I mean, so that's 50 over 200, like so. Okay, now that we have found that, we have to divide it by the probability of finding someone who is a driver at all. So what's the probability of finding someone who is a driver here? Can someone help us out? What's the probability of finding a driver?
A bus driver, eh?
Yes, please, a bus driver.
It is 125 over 200.
That's correct. 125 over 200. Excellent. Okay. So then the probability of finding someone with a bus driver is the number of bus drivers. As you can see here, the total number of bus drivers is 50 happy ones plus 75 unhappy ones, and then the total is 125. So probability of finding someone who is just a bus driver is 200, 125, where the number of bus drivers over 200. So now when we do this now, right, we are going to be able to calculate what the question is demanding for. So then let's do that. 50, let's simplify these things. 50 over 200 simplifies to 1 over 4, right? Okay, let's just go ahead and do the work and it will simplify itself. So then in division of fractions, 50 over 200, division can be written over as a multiplication And then my math teacher will tell me back in school that you rokoto it. So then what was 125 over 200 becomes 200 over 125. You'll be using a calculator, by the way, so you don't need to do all these things, right? But you still, I guess it doesn't hurt to know. So then we can simplify this way. 200 crosses out 200. 25 goes here 2 times, and then 25 goes here how many times? 5 times, right? So in the end, we are left with 2 over 5. Or that also simplifies to exactly 0.4. Since 5 goes into 24 times, then 2 over 5 is the same as 0.4. So this is basically what it means to calculate such conditional probabilities. I hope we are clear. I want to give you an example. So now we just calculate the probability of finding a happy person, given that they are a bus driver. What's the probability of finding someone who is a bus driver, given that he is happy?
The person is a
What's the
bus
probability?
driver, right?
Yes, but then the given probability is that he is happy. How do we write the formula for this one?
Okay. So the formula is
Make some space. Okay.
probability of bus driver intersection happy.
Okay, probability of a bus driver is driver intersection happy.
All over probability of happy.
Oh, thank you. All over probability of happy. Probability of happy. Exactly. So this is going to be the formula if this is what the question intended for. And then we solve. So then this time we do the same thing. We find the D intersection H, which is still 50 by the way. And then we also find, so 50 out of 200 is the intersection H. That simplifies to 1 over 4. So let's just write 1 over 4. And then we divide it by probability of finding someone who is happy at all. And how many people are happy? 50 happy drivers, 40 happy lawyers. Adding that together gives us 90 happy people. So then we divide this by 90 over 200. Hey. 90 over 200, like so. Very good. Okay, I'll simplify this a little. So then this is going to be 1 over 4 times 20 over 9, right? What goes here? 1. What goes here? 5. And then we are left with 5 out of 9 as our final answer. So this is if the question asks us, you can see they are giving us different values. When we did H given D, what we got was 0.4. And now we've gotten 5 over 9, which gives us something like 0.45 or 47 something, right? So there is a difference, a clear difference between the two. Do not confuse them. So the given one, the pre-established one, that's the first one. They said given a bus driver becomes this guy, and that is going to be your denominator. And over here, this question asks for given that they are happy. That's why I used H here, and then the denominator is H. All right. So now, are there any questions you would like to ask before we proceed? As I said, if you have a question, ask early before we go further into the lesson. There is no shaming whatsoever here. If you like, do not disclose your name when you're asking the question, okay? You can even, what do we call this? Change your voice and just ask before we proceed. Okay, please, is there someone who wants to speak? You may go ahead and speak. I can hear an unmuted mic. Okay, looks like the person might be facing some challenges, so they are just not, it's a mistake. Okay, so I'll assume that everybody here gets it down to their bones, so nobody needs to ask any questions. Let's proceed. That's what you can see here. So here, 0.4, that's what that simplifies to. Okay. Now, here's another question. There are 8 boxes, 3 of type A, 5 of type B. Type A boxes each contain 3 green marbles and then 4 red marbles. Type B boxes also contain 2 green marbles and 4 red marbles. A box is selected at random. A box is selected at random and a marble is drawn at random from the selected box. We have to find the probability that that marble is red. Okay, so then we have 8 boxes. 3 of them are type A boxes, and 5 of them are type B boxes. Type A boxes have 3 green marbles and then 4 red marbles. Type B boxes have 2 green, 4 red. Now we are saying that we have raised into a random box. We didn't look at the box. We just raised into one of the boxes. It could be red. It could be A. It could be A. It could be what we call it B. And after reaching into it, we pick the random ball too. We don't know whether the ball is black or is green. All we know is that we are trying to find out the likelihood of that ball we picked at random from a random box, right? Is going to be red. For this one, it's very important that you know it's different from your average probability question. So don't just go and take number of red balls over total number of events. Remember, there are 2 separate events here. You can either pick the red ball from a red box, on an A box, or pick it from a B box. You see that? Therefore, if you want to calculate the probability of picking a red ball, we have to know probability of taking a box first, that is red, and also opening that box and taking, sorry, you have to know the probability of taking a box that is an A and opening it and taking a ball that is red. And we have to also know the probability of taking a box that is B and opening it and taking a ball that is red. And then adding these 2 together is what is going to give us the probability of getting a red ball, actually. I hope this makes sense. Does this make sense?
Yes,
It makes
yes.
sense. All right. It makes sense. It makes sense to me, actually. Don't do me out. Anyway, as I was saying, we have to know the probabilities of the red ball coming from both boxes so that we can combine them to know the probability of both events happening. Okay, I need some space here. Let me see. Can I create some space on this thing? Is there? No, certain. I'll have to open a board. I don't want to waste time doing that. So here's what I'm going to do. I'm just going to solve it right here. So let's try this. This means that we have to, the probability of selecting a red ball like this. Let's RB red ball as it says. Let's RD notes and red ball, red marble, whatever. Probability of selecting a red ball is going to be, first off, probability of taking a type A box and taking a red ball from the type A box, plus probability of rather taking a type B box and taking a red ball from that type B box. Combining these 2 intersections is what is going to give you the probability of really getting a red ball. So then now we take into consideration that the fact that it can come from A, it can come from B. So then the first one is talking about the fact that we first picked a type A box and then open the type A box and then pick the red. Second one is talking about the fact that we first pick the type B box, open the box and pick the red. So then the probability of picking a red at all is going to be what we get when we combine this with this. I hope that is clear. Yeah, like this. All right. So then let's first calculate the probability of taking a type A box and a red box as well. Okay. So this means that we need to know the number of A boxes, the probability of A box, and multiply that with the probability of red boxes, right? So what's the probability of picking an A box? Let's find that. Oh, sorry. Let me see. So then we need to know the probability of picking an A box and probability of picking a red. But then you can clearly see that that will not be as simple as it's supposed to be, because the reds, as we mentioned, some of them are in the boxes of A, some of them are in the boxes of B. Okay. We can go ahead and use the formula that we saw on the earlier slide for finding the intersections only. If you remember, there was a formula for finding intersections like this. The formula that stated that you can manipulate the combined probability and the conditional probability formula to get intersections, where your probability of A intersection B or A intersection R in this case can be rewritten as probability of taking an A probability of taking a red ball, provided it comes from an A box, all times the denominator, which is still the probability of A, like so. So probability of picking a red ball, given as you picked an A box, and the probability of A. Remember, this goes back to the formula that we stated far earlier on. Look at it. This formula we stated way back here.
Sir, please, the place that you are writing on is dark.
Yeah.
We can't see it.
It's dark. Oh, you can't see. Oh,
Yeah.
sorry. It's quite clear on my side. Oh, sorry. Then I'll raise it up, okay? All right. But then we are talking about this formula right here. You see the intersection here clearly shows something. It clearly shows that this side, the intersection here, can be expressed as this A given B times probability of B. Okay, so then this idea is what we are using right now. But you said you can't see, right?
Yes.
Yeah. How about now? Okay, so let's
Right
go.
now,
Can you see?
yeah, I can see clear.
All right. So now let's move. Okay, here we are. Good. Let me remove it from the words a little. So I put it down there so that it will not overlap with the words and then there will be no confusion. I think this side is better, right? Right?
Better is
Yeah,
better.
this is better. Good. So now the probability of A intersection R is the same as probability of R given A multiplying the probability of A. That's what you're saying here. So now let's take all these parameters and find out what they stand for. This will be the same thing for B, by the way, but we are first doing is for box A. Now we are doing this for box B. So for box A, what's the probability of getting what do we call it? A red ball from box A. So now let's go to the question. It says that there are 8 boxes, 3 of type A, 5 of type B. Type A boxes each contain 3 green and 4 red marbles. So the probability of picking a red marble given box A can be directly gotten as the number of red marbles inside the box A boxes. That's going to be 4 out of the total number of marbles inside the box A boxes. That's 7. The type A boxes. Okay, 4 red marbles out of the total number of type marbles inside type A. That's 4 plus 3, and that's 7. So this is the probability of getting a red marble given a count from type A. Is that clear?
No, I'm confused. Can you take it again?
Okay.
Just
All right.
yeah.
All right. Thank you for your honesty, sir. Else I would have gone further, and then you see, we will get stuck somewhere. Good. So now what I'm implying now is this. In order to calculate for the intersection, we have manipulated the formula. And the formula says that we just need to know the probability of taking a red marble, provided that it comes from type A box, and multiply that by probability of picking a type A box at all. If you go
Okay.
back to the question says that inside the type A boxes, it says type A boxes each contains 3 green marbles, and it also contains what? 4 red marbles. So what's the probability of selecting a red marble from a type A box? That's going to be the number of red marbles, which is 4, over the total number of marbles, which is 4 plus 3, right?
Yeah.
And that's 7. So probability of picking a red marble from a type A box only. So probability of picking a red marble, given that it comes from a type A box, is going to be number of red marbles there, that's inside the type A box, 4, over total number of marbles at all in the type A box, that's 7. So 4 over 7 is this side of the operation, this side. That's 4 over 7. And
Can you
also now we find,
shift it like small up
oh,
small?
okay. There, I forgot you even mentioned that. All right. Is it better now?
Yeah, clear.
All right, good. So 4 over 7 for that. And then it says we multiply that by the probability of getting a box A. So what's the probability of getting a box A? As for this, I'll leave it to you. How can we find the probability of getting a box A? Given all the information over here, let me clean some of these things. Okay.
Okay. It's 3/8.
3 out of 8. Excellent. So then, yeah, Mr. Emmanuel, please speak.
Oh, you just answered. I wanted to answer before.
Oh, okay. All right. Thank you for your contribution. So as I was saying, So for the probability of the red, that's going to be number of red type A boxes, sorry. Probability of picking a type A is number of type A boxes over total number of boxes, and that's 3 type A boxes, right? Over the total number of boxes, which is 8, as you can see here. So we can multiply them to get our final answer. So 4 times 3 gives us 12. And then 7, 8 gives us what? 56. We can simplify this, can't we? Yeah, we can. Yes. So then what's the simplification? We can start with 2. 2 goes here 6. 2 goes here 28. 2 also goes into 28 14 times, and it goes into 6 3 times, right?
Yeah. So I can't hear you. It's my network. So I can't hear you.
I think he's not talking now.
Okay.
Hello, sir. Am I audible? Can you hear me?
Yeah, we can hear you clearly now.
I'm so sorry. My data just expired, so I had to just buy some. Wow.
So sorry.
All right. Data na shi o, bema ashi.
Yeah,
Okay. Okay. Let's get back to it. All right. Back to what we were talking about. What were we even talking about? Good. Yeah, our calculation. So we said that this will lead us to 3 out of 14, as you can see. So then it means that for probability of getting A, provided picking a red box and picking an A box, sorry, probability of picking an A box and picking a red is 3 over 14. So now that we know that, let's keep that in mind, and let's go and look for probability of picking B intersection R. Okay, so we've already found the first part of it. Now let's find the second part of it. Now I want you to take note of the fact that you see this is a long working, right? See how much time is taking. But then when it comes down to it, the concept is simple. We are just finding the intersection now, adding that to B intersection now. It's just that it takes more than one step, and then it will seem tedious, but then it isn't. Keep that in mind. So let me keep this one right up. Let me see something. I will copy that, delete it, and then I can move this one somewhere else so that I can put it here. All right. Okay. Then we know that the probability of A intersection R is giving us 3 over 14 right here. Good. So now let's find the probability of B intersection R, shall we? So the probability of B intersection R will also follow the very same approach that we followed for A. So for this one, I want one person to mute their mics and walk us through. Okay, this time let's take someone, Mr. Caillou. Okay, you have been very contributive, but let's try another person. Yeah, I want to see if we are really following or if Mr. Caillou is just a serious shark that doesn't want. He's doing a low key, right? So can someone walk us through calculating probability of B intersection R? Oh, okay. Yeah, Mr. Emmanuel Kote, let's go.
B
Uh,
intersection
Your
R.
yeah,
Yes. So in
yes.
type B, 6
Oh,
marbles.
sorry, I
So
can't. Your network is breaking up. Sorry, so come again.
in type B boxes, there are 6 marbles.
Okay.
Oh my God. Come on.
Oh, I can hear you. I can hear you. Okay. So he says that we have to find. He said in type B boxes there are 6 marbles. All right. Continue. Mr. Naima, we are listening. Oh.
Hello.
Yeah, we are listening.
So I'm saying, yeah, yes, please, sorry. It was my network.
Yeah.
So I'm saying in type B boxes, there are 6 marbles.
Okay.
So they contain 2 green marbles and 4 red marbles. So the
Okay.
probability of B intersection R will be over 6.
Okay. So please, I want you to
Which is
pause there a little. Mind you, that is not probability of B intersection R, okay? That's rather B given R. So I understand where you're coming from, but then this is the probability of B given R. The intersection is what you see over here. You see that's a little difference. If we talk about intersection, right, it has to do with the number of type A boxes there. Remember that in every type A box, yes, there are 3 marbles out of 6. Hey, there are 4 marbles out of 6 that are red and etc. But then if we want to consider how many type A boxes are there are a lot of them, right? So then the intersection is different from how many red marbles are in a type A box. That's just the probability of a red marble in a type A box. But then B intersection R is very different from what we are doing. So what you are describing right now is rather B given R, and that's correct actually. That's what we want. But it's not stated as the intersection. Okay, so please do not confuse the two. So yes, Mr. Emmanuel has stated it right. He says we take the probability of
Please, can you
picking
take it again? It seems like I'm confused a little bit.
confused with and what I just said, right, concerning the intersection and
Yes,
then the
please.
conditions. All right, let's look at it this way. Currently, the boxes that we have here for type A, there are 1, 2, and then there are 3 boxes. These are all type A boxes, by the way. In a type A box, you will find a number of red marbles. So how many red marbles are in a type A box? 4. And then so let me say 4 red. And then you can also find a number of green marbles as well. And that is 3 green, like this. That applies to all the type A boxes. They all have the same 4 red, 3 green, 4 red, 3 green. If I ask you for finding the probability of a red marble intersection type A box, what am I asking you for? It's different from saying what's the probability of going into a type A box and picking a red marble. That one will be giving us probability of R giving a type A box like this. And let's see why these two events are different. This one says we are just going into any of the type A boxes. So if I go into type A box like this one, the probability of taking a red marble from there is just going to be the number of red marbles, which is 4, over the total number of marbles, that is 7. And that is what this probability is about. A probability of picking a red marble and picking a type A box is separate. So this means that we have to first consider probability of picking a red marble from the type A box, and we already know that to be as 4/7. And we see probability end talks about what multiplication, right? So it's going to be probability of picking a red marble, which is 4/7, times probability of picking a type A box. And then to pick a type A box, we know how many type A boxes are given. This one considers the fact that the red marble you're picking can come from the first type A box, it can come from the second type A box, it can also come from the third type A box. Whereas the first one only talks about you picking just a single type A box and going into it. So this one looks at a combined probability of all the type A boxes. This one looks at an individual type A box. Does this make sense?
Yes, please.
All right. So then let's see the difference between the intersections and then the conditional probabilities. Intersections cover a broader scale. They take one event times another, provided the events are independent. And that's what we are doing over here right now. So we are saying that we take probability of picking a red ball given a type A box times probability of picking a type A box at all. All right. So then with that information, let's go back to our working. So Mr. Emmanuel was stating, so please, Mr. Emmanuel, come back to me and let's continue.
Yeah, so like you just said, the probability. Yeah, like we said, the probability,
Of
like the
red
number of
giving B.
red given B here will be 4/6.
Good. Says that's 4/6.
Why
So 4. Yes.
the probability of getting a type B box out of the total number of boxes will be 5/8.
Oh, okay. Very good. So 5/8. But then the working is going to be probability of picking a red ball given a count from type B multiplied by probability of picking a type B box, right? That's basically what he just stated. So then that's what you are seeing here. Let me lift this up to this side. Very good. So then if we do the working for this, what do we get? 4 times 5 gives us 20. Or we can simplify first. That makes things easier, right? So 4 goes here 1, 4 goes here 2. And we have 1 times 5 is 5. And then 1, 4 goes here 2. Sorry, so 6 times 2 is what? 12. So this leaves us with exactly 5/12. This leaves us with 5/12, and that's what you can see over here. 5/12. So now we know the probability of what? A intersection R. So picking a red box and an A ball. Picking an A box and a red marble. And now we know the probability of B intersection R. But then we know that the red marble can come from A, it can come from B. Now that we know the two values, then the probability of getting a red marble at all, right, is going to be probability of you picking that red marble from a type A box plus probability of you picking that red marble from a type B box. And that is going to be the first one we got, what, 3/14 is written up there. So 3/14. And we combine that with the probability of picking it from a type B box. And that was what? 5/12. So punch this on your calculator and tell me what your answers will be, okay? If you have a calculator close to you, if you don't, just say it and then we will work it out right here, right now before we proceed.
I think at my end, I can't see it well because I can only see the two thing is at that place. So
Oh, okay. Oh, sorry. I forget you keep mentioning that.
my
So
screen. So
it's small. Okay, don't worry. So let me just lift it for you. Okay. Yeah, that's why you can ask. Don't worry. So how about where can I put this? Here. What about here? Perhaps I should write in a different color so that I can put it over the blacks. Everywhere is occupied. Baby, I am.
yeah,
Right.
you can put this. Yeah. Okay, sure.
Perhaps here is better. Okay. 3/14 plus 5/12. Yes, Mr. Emmanuel, please speak up. Boss Emmanuel, you may speak. Oh.
Yes, sir, please. Just to be sure, are we multiplying or we are adding?
Oh, we are adding the two events. You see, we are taking probability of it coming from an A or probability of it coming from a B. You see the thing? And then we are doing A or B means probability of it coming from an A plus probability of it coming from a B. So we have taken the probability of the red ball coming from an A. That's what we calculated for. And we are now adding that to the probability of it coming from a B. Since we want probability of it coming from A or probability of it coming from a B. And I told you to take notes of these words or. right? And you see, in end, when we're finding A and R, we're multiplying and all. That's what you are seeing. It's basically the same fundamental things we've been doing, just on a higher scale, right? So yes, please, we are adding the two values.
So I
So
got
I'm getting 53/84.
You got what?
53
Sorry,
over 84.
50,
53,
53
53 over
over.
84.
Okay, please, what's that as a decimal number?
Let me send you the.
0.630.
0.63. Okay, 0.63. So then this is the probability of we picking a red marble at all, and that's 0.63. Let's keep that value down, and then let's solve the next question so that we can compare these to the workings, and we'll see if there are any mistakes we made along the way, and then we correct them quickly before we proceed. So 0.63, keep that in mind, 0.63, 0.3. So I hope it's clear. I understand it's a lot, like seeing us is just one question and it's taking a lot of time, but when it comes down to it, it is just bulky, but it's actually simple. You see, it's the same thing, like it's a simple concept, right? It's just that it has a lot of steps, but then it's simple. That's all there is to it. It's bulky, but it's simple. So then we just found the probability of picking a red ball to be 0.6 and 3. So that's the first question, I. Now let's move on to II. Someone is unmuted and then the person is talking. Please use your mic. All right. Let's proceed. So a marble was selected and was found to be red. So now we have finished the first question. Second question says a marble was selected and it was found to be red. What is the probability that it came from a type A box? A marble was found to be red after it was selected. What's the probability that it came from a type A box? So what do you think are the parameters we need over here? We are trying to find the probability that we have selected a red marble and it comes from a type A box. So now we already selected a red marble, right? The condition at hand is it comes from a type A box.
Okay, can I try some?
Yes, please. So what would the formula be? Let's start with that.
So probability of it coming from type A, condition that it is red.
Okay. You want to say type A,
Yeah.
condition that it is red. All right.
Is equal to probability of A intersection red.
All right. All right.
All over divided by probability of red.
Okay. Like this. All right. So then let's plug in the values. So we have already worked A intersection red earlier, right? What did we get for it?
0.63.
Oh no, that's probability of red.
Okay. Probability of A intersection R, right?
Yeah. I have cleaned all that right. Let me see. So A
3
intersection
over
R is
14.
what? 3 over 14 is right. Okay, good. So then that's going to be the 3 over 14, then divided by 0.63, right? 0.63, okay, I've forgotten what we got it from.
53 over 84.
53 over 84, all right, fine. Okay, that's fine. But just punch it on the calculator, you'll be able to tell. So there are two ways this could go. I want to know, are we really doing probability of A giving it red? Like probability of picking a red box giving a type A box giving it has a red ball or something, or we are rather doing probability of R giving A. And then what is the reason for your assumption as well? It's an important question. Just as we showed in the earlier example, the first example, not this one, it shows that both give different values actually.
I think we are finding for probability of A, given that it is red.
Okay, so what is the reason for your assumption?
Because according to the question, it is saying that what is the probability that it came from a type A?
The type A box. Excellent. So then you see the question as he is breaking it down. He says that the pre-given condition or the pre-existing condition that has been mentioned is that the ball was found to be red. You see the term? Therefore, it being red is a pre-existing condition. So we are going to do type A boxes in terms of the red marbles, not red marbles in terms of type A. Because the question clearly stated what the pre-existing condition is and what the probability you are finding is also as well. And that's why we are rather going with probability of A giving red and not probability of red giving A. That's according to Mr. Kayu. So then please, when you punch 3/14 divided by 0.63, what was your answer? You didn't punch it. Okay, let me take out my calculator.
I think it's 0.34.
It's 0.34. Oh, okay. 3 divided by 14.
0.35.
0.35. Okay. And then we divide that by, so since nobody was talking, I'm punching my things, so you have to relax. Okay, 0.34. 0.35 is not so vital. Perhaps you're rounding, right? It's a little exaggerated.
No, after the 4 is
No,
0.
I approximate it.
Yeah,
Okay.
you approximated it, but if you approximate it, you're going to get 0.34. The digit that comes after 4 is a 0. So that still
Yeah.
rounds to
Oh, yeah, hold on.
0.34. Yeah, unless it's 4, 5 or greater. That's when you can round it up.
Okay.
Yes, please. Okay. So now let's compare what we have found so far and see if there are any flaws in our reasoning, most especially for the second question. 0.34. So that's probability of R, 0.63, and then probability, that's II, question II here, like this. Let me clean everything else so that we can clearly see the answers when we move to the next slide. All right. The probability of picking a red marble, wait. Okay, so that's 0.63, so we're correct. And the next one too, yes, it's also worked out its magic, and then it's giving a value 0.33, and ours was 0.34. So perhaps there is, you see, the reason why they are getting 0.33 is because of this value right here. They have approximated their first value, and that is one thing that can affect your working as well. If you overround, most especially if you're rounding values that are not your answer, you're going to end up getting answers that will be slightly different. And if the question has a lot to do with precision, this can actually be marked wrong. 0.33, 0.34, but there's a significant difference. Yes?
You see, if you punch the 53/84,
Yeah.
you get 0.33.
It's 50 watts.
Like the first value before we the first value that give us 0.63.
Yeah.
The fraction was 53/84.
Yeah.
So if you
And that
try,
gives you that one gives you 0.63, yes.
yeah. So if you try putting 3/14 divided by 53/84, you get 0.33.
Okay.
Yeah.
So that's what I'm saying, that the main reason why we are getting a different answer is due to the approximation that we did. So you see the value that we got, the 0.63, right, it's had more places to it. So if you divide the 53 by 84, what you actually get is 0.63095. But some of that has been cut off due to the fact that we just rounded it and got 0.3630. And that's why we are just seeing the slight difference here. And I'm saying in questions where precision is required, mostly when the question doesn't explicitly say how you should round them, sometimes these things can affect your marks a little. And sometimes even it can make you wrong, like entirely, especially in questions when you're working things like chemistry and all, right? So then sometimes I'm just saying, but this is correct actually. This is correct, 0.33, 0.34. This is still correct. Seeing as even they also use approximated values, but then they punch the raw values into the calculator to get the answer. That's why they're getting 0.33. But mostly when you're doing a working, if you have not arrived at your final answer, you are advised not to do estimations. Okay, then again, 0.63 was the answer for the first question, so the estimation was still allowed. So just keep that in mind. So yes, the first working, correct, and then the second one, 0.33, so that too is correct. All right, so then this is conditional probabilities. This is the, what do we call it? Introduction to conditional probabilities. So remember what the formula states. For any given event, in order to express one event in terms of another, is probability of event A given B all over probability of B. Sorry, the probability of A intersection B all over probability of B. That's probability of event A given B, and vice versa for probability of event B given A. Okay, so now that we've cleared that, let's move on. Two events A and B are related in such a way that the occurrence of either one has no bearing on the occurrence of the other, are said to be independent. So yesterday we looked at mutually exclusive events, events that occur without affecting one another, right? We say they are independent of each other. Therefore, we can consider them, yes, to be independent. For instance, now, mind you, independent events are different from events that have intersections, but then they do share some similarity in themselves, right? Some events can have no intersections. Some can have intersections and be considered independent, and some can have intersections and still be considered dependent as well. Some can be without intersection, that was I'm implying, and sometimes be considered dependent. For instance, if a coin is tossed repeatedly, the results of one toss does not affect the results of another toss or any other toss. Alternatively, we may say two events A and B are independent if the knowledge of the occurrence of A in no way influences the probability of the occurrence of B and vice versa. So can you give me examples of two such events? So, okay, let me give you a clear example and you also build an example. Let's say I'm watching a football match and then I'm eating rice, two separate events. There is no correlation between my eating rice and the football match. Nothing happening in the football match can make my food, can affect my food. Unless, of course, it angers me and I punch it. But then still, the two events are not dependent, as I am stating. And also, nothing I can do to my food will affect the football match. Therefore, the two events at hand, me eating and watching the football match, or the football match that is ongoing, share no correlation. Therefore, we say they are independent events. Okay? Statistically, events A and B are said to be independent if and only if the probability of A intersection B is equal to the probability of A times probability of B. What this means is that for an event to pass as an independent event, when we calculate for its or when we are given its intersection like this, it should be the same as what we get when we multiply event A by event B. So this only applies to events that have no common ground in between them, events that have no intersection. So it says, in order for you, so if a question can be given to you and then you can be asked that, are these events independent? In order to find out if they are, you have to multiply their probabilities to see if it gives you the same answer as their intersection. So for example, in the question of a Ludo die toss, if I ask you that the probability of an even number occurring, and then the probability of an odd number occurring, are they independent events? if they are independent event, then it means that when I try to find their intersection, it's going to be the same as what I get when I multiply both their probabilities. If the two do not give me the same value, then I cannot consider them independent events. It means they are dependent. But that's the whole idea. Let's look at the examples on the next slide. And then if there are some workable ones, we will work it so that it will establish the understanding. Just as I did yesterday, I'll put some questions on the page. Doing them as polls is too taxing. Tasking, yeah. But all right, I'll do that. Let's move on. So now, if it follows from the definition of a conditional probability that if event A and B are independent, then the probability of A given B is equal to the probability of A, and also probability of B given A is equal to the probability of B. And why is this? If two events are independent, then it's most likely that their intersection, right, is equal to what you get when you multiply A as well as B. So then it says that for an event A to occur given B, it may be simplified into probability of A, and then for probability of an event B to happen given A can be simplified into a probability of B. What this tells you that if you are solving a question and you are told that the events are independent, you don't have to go through the trouble of solving for this when you've already been given this. Because even if you solve for this, eventually you're just going to arrive at the same probability of A. So they're telling you that if you are solving and the question tells you that these two events are independent, then your A given B is just going to be probability of A, or your B given A is also going to be probability of B. You know why this is happening actually? Let's consider these things and see why this is happening. You see, if I tell you that two events, probability of A, right? Let me use decimals. That will be easier to express. If I tell you that the probability of two events, maybe A is something like 0.5. 0.5. As for me, I'll explain everything to you. So whether you like it or not, we'll be wasting time on these things, but you have to understand so that you don't forget. If the probability of A is 0.5 and then the probability of B is something like, let's say, well, I want to use values that sum up to the same thing, to 1. Okay, so that I cannot be a biased teacher, as I'm here stating that probability sum up to 1, blah, 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 whatever that. So 0.4, and then the probability of B, let me modify this and make it into a B. Yeah, okay. And then probability of B is given to be something like 0.6. If I tell you that the two events are independent, it means they share no intersection. Then if I want to find the probability of A and B happening, that's probability of A intersection B bracketed like this. It's just going to be probability of A, which is 0.4, right? Times probability of, so 0.4 times probability of B, which is 0.6. Now keep this in mind, okay? Now, if I want to solve for probability of A given B, what am I going to have? I'm going to have probability of A intersection B all over what? Probability of B. So I'm trying to solve for this, as you can see here. Probability of A given B. So it's going to be 0.4 times 0.6 all over the probability of B. And the probability of B, which we already know to still be what? 0.6. And see what funny thing happens here. 0.6 cancels out 0.6. And in the end, the last man standing will still be probability of A. So what this means is that for independent events, right, the probability of A happening given B is still the same as probability of A, since your intersection is just going to be A times B. And also, inversely, probability of B given A is still the same as probability of B. Am I explaining into detail? Like, do you understand what I'm getting at? I find it fascinating. That's why I'm teaching you, so that you also keep it in mind. But I think you could have lived this day without knowing this. So if it has bothered you, I'm sorry. But still, get the idea down. Okay. The reason why probability of A given B is the same as probability of A is this, what you are seeing on the board. And that's the same reason why probability of B given A is probability of B. Do you understand this?
Yes.
Right. All right. I like that. Okay. So then let's move on. Now the tests for independence. So let's test to see if these countries are independent. The test for independence says the first one is what we have looked at, that the probability of A intersection B is going to be what? The same as probability of A times B. Now, what if we have more than one in the event? What if we have an event A, an event B, and an event C? Then the probability of this event being independent, or then the event being independent, is going to be the probability of this is the tests, and these are the steps of the test. A intersection B should be the same as what you get when you multiply probability of A and B. After that, A intersection C should be the same as what you get when you multiply A and C. After that, B intersection C should also be the same as what you get when you multiply B and C. That's for 3 events. And finally, when you combine A intersection B intersection C, it should be the same as what you get when you multiply A by B by C. Okay. You see she crying. All right. Let's move on. So now let's see how we can apply this to a question in the next slide, okay? I copy this. Okay. Like I would like to copy this and take it to the next slide. Oh shit, they've already worked it. Okay, so now let's test these things out. So it says that a ball is drawn at random from an open box containing 4 balls, numbered A and 1, 2, 3, 4. Now let's add what we call it, 3 events happening in that set. The events A is 1 and 2. So let's say we drew 2 balls, right? And after drawing the ball, one event says that maybe we drew the ball with the number 1, and then we secondly drew the ball with the number 2. Let another event say that maybe we first drew 1 and then drew 3, and let another event say maybe we first drew 1 and drew 4. Now, we are supposed to test for the independence of these things. Are we clear? I'm going to capture this, take it to another screen, all right, so that we can solve it, and then in the process, get to understand the concepts better. Otherwise, we'll just be looking at the answers and smiling, thinking that we've done something, but then in the end, we do nothing. Okay. Okay. So is there blank space? Okay, we can use this side. Okay, forget all the formulas and whatever. We can paste that. Okay, sorry, you pressed the wrong key. Ended up on the wrong page. Okay, let me go back to the place. All right. So this is the snapshot we took, right? Copied it over. Good, 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 good. This is a snapshot we took. Where can I paste this? Okay, then I guess we are just going to have to use it because I'm unable to paste it. So now let's do the working right here, shall we? So then it says a ball is drawn at random from an open box. And then the open box containing 4 balls right here, and then blah, 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 etc., etc. Now we are supposed to test for independence amongst all these elements. Now, in order to test for the independence of all these elements, we are going to have to follow the rule that says we have to, if in order for the event to be independent, probability of A intersection B should be the same as what? The probability of A
of A times.
yes times B. Can we see? I hope you can see my screen, or you can see.
Yeah, we can see it.
Thank you. Thank you for that affirmation. All right. A little H. I did that. Let me share this window instead, and then you can see it clearly. Where am I? All right. Okay. Oh, I'll share in the window, but the window is not sharing. Yeah. You even if you can see a little boss, I am begging you, okay? Let's just take it as it is. Okay. Right, so we continue. So then we are testing to see the probability of A intersection B is the same as probability of A times B. Remember, this is just one of three conditions. We are testing for three separate events. If it was just two events, then this would have been enough proof. But since these are three separate events, there are three steps. We have to check if A intersection B is the same as A times B, and A intersection C is the same as A times C, B intersection C is the same as B times C, and finally test if A intersection B intersection C is the same as A times B times C. Okay. So now let's test all these things. First off, if you go to the question, what is A intersection B? So according to the question, it says that for this event, when the ball is drawn at random, A is 1 and 2, B is 1 and 3, and then C is 1 and 4. What is the intersection between A and then B? Can you tell? So what's that defined intersection? Which number here is the intersection? Let's be fast. Our time is almost up.
It's one. One is
It's 1. Very good. This means of the universal set. Ebenezer Nyako, yes, please, you may speak.
So that's what my brother said. Thank you.
Oh, okay. All right, boss. Thank you. Thank you for the contribution. Okay, as I was saying, what this means is that 1 is the intersection. Therefore, the probability of that intersection is going to be the number, how many times 1 occurs out of the universal set. That's 1 over 4, right? So then the probability of the intersection happening is going to be 1 out of 4. So let's do that. So the probability of intersection B is going to be what? Maybe let's replace these things with that. So it says it's 1 out of 4. Now let's see if 1 over 4 is equal to probability of A times probability of B. According to the question, the probability of A is what? 1 and 2. So the probability of A happening is those two events over the universal set, right? That's going to be 2 over 4. Let's keep that in mind. And also, we are multiplying that by the probability of B. B is also 1 and 3. And the probability of B occurring is these two events out of the universal set, which is 4. So that's also what? 2 over 4. As you can see here. So now let's test to see if this gives us the expected answer. Let's simplify first. 2 can go here once and go here 2. That's 1 over 2. This is also 1 over 2. We also here 1 over 2, sir. So 1 over 2 times 1 over 2. 1 times 1 gives us 1. And then 2 times 2 gives us 4. So then we have been able to prove the first side of it. The probability of A intersection B is the same as, what do we call it? A times B. So this only means that A and B are independent events. If we've tested the first one, we have to test the same thing for B and C. But then for B and C, we are going to follow the same principle. For B and C, sorry, let's do A and C first. The intersection they share is also 1, right? So it's still the same 1 over 4, like this. And then we do probability of A times probability of C. That's still going to be 2 over 4 times 2 over 4. And that's still going to give us the same answer we got, 1 over 4 again, like this. We do the same thing for B intersection C. B and C share the same thing, 1, 1, right? If we calculate it, we are still going to land at the same 1 over 4. Now we have been able to confirm that A and B are independent, A and C are independent, B and C are independent. In order to check whether all three of them are independent, one last rule must be fulfilled. That rule says that, let me clean all of this, please. Okay. That rule says that in order for these guys to all be independent, then this must happen. The probability of all three events happening, that's probability of A and B, and C must be equal to probability of A like so times that of B. Get the idea, right? The same thing. We are testing independence to those who are confused or lost. And probability of C, like so. So now let's check this to see what is probability of A intersection B intersection C. So what is there an event that occurs at all three places? Yes, one occurs here, and occurs here. So one is that combined intersection, right? And since it's just one element out of 4, then the probability of A intersection B intersection C is how many ones we have here? That's 1. Out of the total number of events here, that is what? 4. Let's equate that to these multiplications and see if they give us the same value. If they don't give us the same value, then it means they are not independent. So we are supposed to get 1 over 4. Probability of A, we checked that it was 2 over 4, right? That's the same as 1 over 2. Probability of B is also 2 events out of 4 events. That's also the same as what? 1 over 2. And then probability of C is also the same as 2 out of 4. That's also what? 1 over 2. So if you multiply the numerators, 1 by 1 by 1 gives you what? 1. But 2 is 4. And 4 2 is 8. But look at this. Oh my God. So the 8 is different from 1 over 4, right? What will our conclusion be? A, B, and C are not independent. So they are actually dependent events. So this is how you test for independence. Okay, you find the probability of 2 events occurring, and then when you're done, you compare these ones to the probability of all 3 events occurring. They have to all be the same as were stated in the sets. So the intersection were already stated. We have just tested to see if the multiplications give us the intersections. It showed us that A and B were independent. It showed us that B and C were independent. It showed us that A and C were independent, but it has proved that A, B, and C are not independent. Therefore, we can conclude that these 3 events are not independent. Is this clear? And for any given question, I believe you should be able to apply this and then test for independence. Is this clear, people? Is this clear?
Yes.
Okay.
Yes, sir.
Okay. All right. I'm communicating. I hope I'm communicating. All right. And we proceed. So now let's look at what the required workings were supposed to be. So when they do the testing, yeah, they get the values 1 over 4. So, but then the final one, it shows that after they multiplied, right, they give you 1 over 8. And that is not equal to the A intersection B and C, which was 1 over 4. Hence, we conclude that A, B, and C, right, are what? Pairwise independent. Pairwise. This one here, avocado, is implying that when you combine them, that A and B, they are independent. A and C, they are independent. B and C, they are independent, as we proved earlier. But when we put all 3 of them together, jointly, they are mutually independent. So they are not independent. So in other words, they are dependent. So A, B, and C are pairwise independent, but not jointly or mutually independent. Thank you for being a great students tonight. My name is Prince Wilson. We have brought the lesson to an end. Our time is up and we have to leave. I will make room for questions. Go ahead and ask your questions. Before you ask your questions, some of you have made it into the meeting and I think some of our coordinators have mistakenly let you in. You don't worry, I have seen you. But it's all good. At least we are learning, and that is all that matters at this point, right? So if you have any question, feel free to ask. But if you would like to join us, subscribe to our plan. These classes, they go beyond this semester. Even in semesters to come, we will be doing that. During the vacation, we will be covering classes for coding. The TA for the mirror course of this year, 104, has reached out to us, and he says that the course is one that is quite tedious. It requires, if not mastery, proficiency, a little proficiency in programming languages, including C++, Python as well, and some other languages too. And then we all know that actually, even the little C++ that we were learning, some of us were stuck at installing the IDEs. So we are going to present this opportunity to you, and then we are going to carry on. Yes, Auntie Vida,
Yeah,
please
please.
speak up.
My question is not related to the statistic, but I want to
Okay.
find out if your Oracle account is working.
My Oracle account has been working for a long time, but I don't remember the last time I went into it. I won't lie to you. So
Yeah,
yes,
because I went there right now and they are saying that access denied by application security check.
wait, so access denied by application security check.
Yes, please.
And you are certain you are logging
Except
into like the academy. Like see, there are different
I've
login.
logged into everything. Just that the site
Wow.
it will open. I've been logging in for some time now.
There is something I noticed. At first I used to be able to join.
Then I've joined before. I've been
You've been using it.
learning
Oh, I'm
like
aware.
yeah, I've been using it
I'm implying that
ever since
recently,
he opened the distance. Pardon?
yeah, recently I also run into a similar problem. My Microsoft account, the one that was given by the school, it is unable to join or subscribe for things or make any registration on my phone anymore. At first, I used to be able to use it to create meetings and join and all that, but nowadays I'm unable to use it for such meetings. So I have a feeling that it might be a problem from the email side.
Okay.
But then that aside, it might actually be with the Oracle. So I'll check after the class. And if it's a problem, maybe we can reach out to Mr. Michael.
All right. Thank you.
Okay. All right. You too. All right. So as I was saying, if you are interested and then you would like to build capacity, these are capacity building courses. Charlie, all your IT students are these statistics and cons and things you are learning. They are important, so but then they make up about 1% of your career. Let me tell you. Most of your career, all these things, well, they will be provided for you by other things. Like nowadays, you can use AI for coding and all, but then you all know the fact that yes, AI also makes some mistakes because the instructions that you give it sometimes are not well defined. It's not like it makes mistakes. It creates the program, but then the program might not be to your specification. So this is where you will have to apply your programming knowledge to edit the code that the AI has written. Now, where do you apply knowledge that you do not know? That's why as an IT student, you have to equip yourself with things outside these classes. And then finally enough, the programming that is one of the core of IT is one of the most talked about topics. The TA has reached out to us, as I said. Join our course and then trust me, you won't regret it. If you are into this session, you can see that we are doing our best to teach you on a level where it's student friendly or learner friendly as possible. Join us. And then the thing be you can say 50,000 crowd. So between each year, but then it's not up to 50,000. It's kind of crying drawing be. So then if you would like to, you will see our numbers on our flyers and on our communiques. Just subscribe and reach out to us and then subscribe for our course and then we will make it worth your while. It's been a great night, people. If there are no further questions, then the meeting is adjourned. Tomorrow we'll be meeting same time for economics, 7 to 9. Let me see you there. Mr. Isaac Quinn will be taking us through, and you all know that this man, powerful tutor. Okay, goodbye and then good night, guys. Abigail Dede, nah, please speak. Are you able to unmute yourself? Let me
It was a
tell you.
mistake, please.
Oh, okay, all right, okay. Okay. So then the meeting is adjourned, guys. We have closed Obia and Koda, and then I'll put some questions on the platform. This time I'll put one question at a time, and you do the working, and then like in your own time, and you keep your answer. If you're unsure of your answer, you can upload it, and then we can see where the problems are with the answers. Goodbye. Good night.
Please, I'm not on the platform.
Oh yeah, I'm going to add you to the platform for the makeup class. Okay. The
Okay.
platform for the makeup class. I'm going to add you to that. Right. Goodbye. Good night.
Okay.